So we renamed 5.7. Instead of the rational zero theorem, we renamed it solving polynomial equations by graphing. I showed you how to use Desmos and how to solve equations. The Xintercepts provide answers. Today, we're going to call this part B, or the second part of the lesson. But instead of solving polynomial equations by graphing, we're going to use graphing to factor polynomials. Okay, we're going to use graphing to factor polynomials. And also, there's a final part in our notes, the complex conjugate. This guy right here, we're going to talk about that in the later part of today's lesson. Right now, let's just jump to our worksheet, the 5.6. The first half of it was, doing synthetic substitution, plugging in your input, getting out your output. But the second part, that's where they give you a polynomial function and they give you a factor. Right here, they're telling you that x minus 3 is a factor of this cubic polynomial function, right? And they want you to find the other factors. So I want to really dive into Desmos and explain how the graph tells you what your answers are going to be and how many of those specific answers you actually have. I know that sounds weird, but if you type this in correctly into Desmos, you will have this graph right here, okay? Now, I want to talk about how the x-intercept, the way it crosses the x-axis actually matters, okay? So let's say you have a graph and you see, let's say that it crosses at -2. And when it crosses at -2, let's say it crosses like a perfect line right through -2. Then that answer right there would be x equals -2, and it doesn't have duplicity. Okay, it does not have duplicity. It just crosses, it's just one single answer because it crosses like a line right through it. Does that make sense? Now, if we have, let's say a graph, let's say it's coming down and then all of a sudden it touches at -1, then it goes back up, then yes, the answer right there is x equals -1, but that does have a duplicity. And the duplicity could be of 2, or it could be of 4 or 6. It has an even duplicity, right? And you could remember that because a parabola has y equals x squared. So remember, if it touches, that means that the answer could be repeated twice. Could have a duplicity of 2, could have 4, 6, but let's just stick with the number 2 right now because it could have 2 of the same answers. Now, if it crosses like a line, then obviously just one answer. There is no duplicity. It's that single answer, x equals -2. If it touches, it could have that answer, x equals -1, 2 times. The answer here, according to this graph that we just typed in, the answer is positive 3, right? The answer right here, that's x equals 3. But if you understand graphs, it didn't cross like a line. If it did cross like a line, that would tell me that I only have one single answer, x equals 3, and that this third degree equation has to have 2 imaginary answers to have a total of 3. But it doesn't cross like a line. It doesn't touch like a parabola. That would have duplicity maybe of 2, but it actually crosses kind of like a squiggly snake-like curve, kind of like a cubic function. Does that make sense? So that tells me that this answer, x equals 3, has a duplicity of 3. Pretty crazy, right? But what I want you to do is just start relating that if it crosses like a line, whatever that x-intercept is, that's your single answer. If it touches on the x-axis, that's your answer, but it could be twice. Right? Technically, it could be 4 or 6, but this could be twice because it has a duplicity of 2. And this guy, if it crosses like a cubic function, yes, it only has one answer, but that single answer could have a duplicity of 3 or 5 or 7, an odd degree duplicity. Now, obviously, these guys over here aren't part of the actual graph on Desmos, right? I typed this in. What did I get? I got that single x-intercept, but we know it's not a single answer because it doesn't cross like a line. It crosses like a cubic function. So that's telling me that it could be x equals 3 repeated 3 times, especially because this is a power of 3. I need 3 answers. So this has to be x equals 3 repeated 3 times. So let's go back to the question itself, and let me show you algebraically how it will be repeated 3 times. Now, if we know that this polynomial function has this as one of its factors, then if I divide the polynomial by that one of those factors, I'm going to get the remainder 0. Everybody agree with that? Yes? I hope you guys are paying attention, right? So let's actually divide using synthetic division. Let's plug in that positive 3, because if I were to set this equal to 0, x would equal 3. That's why I'm plugging in a positive 3. My list of coefficients, there's a 1 on the x to the third, there's a negative 9 on the x squared, there's a positive 27 on the x, and there's a negative 27 as a constant. We have this line right here. As you go down, you combine. 1 plus nothing is 1. As you go up, you multiply. 3 times 1 is 3. As you go down, combine. Negative 9 plus 3 is negative 6. As you go up, multiply. 3 times negative 6 is negative 18. As you go down, combine. We end up with a positive 9 right there. As you go up, multiply 3 times 9. That'll give you a positive 27. And of course, the remainder is 0. And it has to be 0. If we know that this is a factor, then we know that the remainder has to be 0. Whenever you divide anything by one of its factors, there is no remainder, right? 12 divided by 4, there's not going to be a remainder. The answer is 3. There's no remainder. Same thing here. They're telling you this is one of the factors. Synthetic division, you should have a remainder of 0. If you don't get the 0, go back and check your work, find your mistake, because these numbers are essential. These numbers are what matter. Again, we're not comfortable factoring or solving to the third power, but we should be very comfortable solving quadratic equations, right? Or factoring quadratic equations, right? Or factoring quadratic polynomials. And when you use a factor and you get this depressed polynomial, what you want to do is make sure that you get to an x squared, because we know how to deal with x squares. And right here we do have an x squared. This is a 9, this is a negative 6x, this is an x squared. So we have a depressed polynomial, x squared minus 6x plus 9. And I could factor this. What does it factor to? Anybody? So that is correct. Negative 3 and negative 3, that's what belongs in here, right? And we have factored the depressed quadratic trinomial. So they're asking us to factor, right? We have factored. What does this mean? They gave us the original one, x minus 3. If I write it over here, then this is the completely factored form of the original. This binomial times that binomial times that binomial, if you actually were to distribute, combine like terms, distribute, combine like terms, and do all that math, this will be your answer, okay? This guy right here is the same exact thing as this guy, but this is in factored form. Now, look at that factored form. Isn't it the same binomial repeated 3 times? It has a duplicity of 3. Make sense? Cool. So I hope we're starting to understand how to get information from graphs. Once again, if it crosses through, then that answer, x equals negative 2, that's a single answer. It's not going to have duplicity. If it touches, then it could have a duplicity of 2, technically of 4, 6, any even duplicity. But look at your original polynomial, and that way you'll know what's going on. Like, for example, this one right here, we knew that it had the degree 3, so I'm looking for 3 specific answers. And when I looked at the graph itself, it was just this single answer, and it didn't cross as a line. It crossed like a cubic function. So that must mean that it has a duplicity of 3. It repeats 3 times. Cool? Now let's say it wasn't a degree 3. Maybe if this would have been a degree 5, and all I got was this, then yeah, this probably has a duplicity of 3, and you have another 2 answers that might be imaginary. Make sense? Anyway, we'll get to those later. But I really want you to understand how to interpret graphs where they intersect the x-axis. If it crosses through, that's a single answer. If it touches, it has duplicity of 2. If it crosses like a cubic function, it has duplicity of 3. But technically, it could be any even duplicity, 2, 4, 6. It could be any odd duplicity, 3, 5, 7, right? Anyway, let's move on. So let's take a look at number 27. We have a 5th degree polynomial, and they give us a factor. The factor is x plus 1, and they want us to find all the other factors. So what we really wish would happen is we graph this on Desmos, and we actually see that it crosses at 5 different locations. Those will be your 5 answers, and we could write the binomials where those answers came from, So let's type this into Desmos. So here it is. Typing it in correctly, you should get this, right? And how many answers do we want on this 5th degree polynomial? How many answers? 5. So if I had 5 separate intersections, I'd be done. But what do I have here? Do I have 5 answers? Yes. I actually do, right? Even though you have an answer right here, that's x equals -2, an answer right here, that's x equals -1, an answer right here, that's x equals +1, an answer right here, x equals 2. Notice what I just mentioned about how it crosses. It crosses as a line. That's a single answer. This guy touches. What does that mean about this answer? Duplicity of 2, right? I mean, and it could be 4, it could be 6, but if you know that the degree is 5, you want 5 answers. 1, 2, 3, 4. Oh, here's the 5th one because it's twice. So this definitely has a duplicity of 2. All right? So how are we going to use these answers to write the factored form equation of that original? Well, it's as simple as this. Let me write those answers down down here. Hold on. Sorry, it's going to get small, but I want to write them down here. X equals -2. We have x equals -1. We have x equals +1. We have x equals +2. I just got those answers from my Xintercepts, right? And I wrote the one with duplicity of 2 in red. Okay, now, where did these answers come from? Normally, we have a polynomial function. We factor it. Why do we factor it? To be able to split them up and set them each equal to 0. So these answers came from a binomial that was set equal to 0. So I need to set this equal to 0 to get that binomial. It's adding 2, adding 2. So where did the answer x equal 2 come from? It came from the binomial. Anybody? That's right. X plus 2 equals 0. Now, this next one, where did the answer come from? X plus 1 equals 0, right? Now, we did say it had a duplicity of 2, so let me write it twice. Does that make sense? Okay, now if I didn't write it twice, I would not be able to get up to the 5th power. So I need to write it twice because it has a duplicity of 2. How about this guy over here? What binomial did this come from? X minus 1 set equal to 0. And this last one right here, where did it come from? X minus 2 set equal to 0, right? Okay, so 0 product property is what allowed us to split them up and set them each equal to 0. So use 0 product property backwards to put them together. And voila, you have your equation in completely factored form. This is it right here. Believe it or not, if you were to distribute, combine like terms, distribute, if you do all that crazy distribution, all that crazy combination, it will give you this 5th degree polynomial answer. But again, all you have to do is type it into Desmos, find your answers. If you happen to have some that have duplicity of 2 or duplicity of 3, please write them twice or write them 3 times. And then just go from those answers, go backwards to get to the binomials of each one that gave you those answers. And that's the factored form. So on 27, it said, here's one factor. Find the other factors. Well, the other factors would be another x plus 1, the x plus 2, an x minus 1, and an x minus 2. Okay? And we did that with Desmos. Let's go back to the notes. All right, so we should know how to use Desmos to find answers. We should know how to use Desmos to take those answers and work backwards to get to the binomials that produce the factored form of each of those polynomials. But right here, there's a theorem. What's a theorem? It's a truth in math. And what kind of truth are we talking about here? We're talking about the truth of complex conjugate numbers when they are solutions, okay? First of all, do we remember what a conjugate is? What is the conjugate of x plus 5? Anybody? That's exactly right. X minus 5 is the conjugate of x plus 5, okay? So when we talk about complex numbers have a real part and an imaginary part. So imagine 5 plus 3i. If you had 5 plus 3i as a solution, then the complex conjugate is also a solution. So if 5 plus 3i is an answer, then 5 minus 3i is also an answer. Does that make sense? Okay. If 2 minus 7i is an answer, then 2 plus 7i will be an answer, right? All you got to do is change the sign in the middle, okay? So if I give you an answer that's imaginary, then you're going to automatically know that the complex conjugate of that imaginary answer is also an answer. Okay, maybe by doing this first one, it'll make more sense. They tell us that a polynomial function has the given zeros, has these given answers. Okay, there's an answer that's x equals negative 5 and an answer that's 3i. Let me just ask you this. What degree would an equation have to be in order for it to give us these answers? What do you guys say? Does it have to be degree 5, 4, 3, 2? Okay, the theorem itself, it is going to be a third degree. The theorem itself says that if you have an imaginary answer, that's an answer right there, that's imaginary, the complex conjugate will also be an answer. So there is no real part in front of the 3i. Like you could have like 7 plus 3i, so the complex conjugate would be a 7 minus 3i. So right here you could imagine 0 plus 3i. What's the complex conjugate of 0 plus 3i? 0 minus 3i, right? So if 3i is an answer, then negative 3i is also an answer. Okay, that's what the complex conjugate theorem says. If 3i is an answer, then negative 3i is also an answer. If negative 7i is an answer, then also positive 7i is an answer. Make sense? Okay, so we have these 3 answers, and in order for us to get 3 answers, we need at least a third degree equation. So like before, let's work backwards. Everybody go leave some space, actually leave a lot of space, all right? And down here put x equals negative 5. And then let's also put x equals that 3i, and also the complex conjugate x equals negative 3i. And why am I putting them down here? Because I'm going to show all my work backwards, okay? See, they want the third degree, they want the third degree polynomial equation that gave us these 3 answers. So where did this answer come from? Pretty simple. Where did the x equals negative 5 come from? Yep, x plus 5 equals 0, and I'm going to put that in parentheses. Where did the x equals 3i come from? Do the same exact thing, just move it over. Check it out. Minus 3i, minus 3i. It came from the binomial x minus 3i equals 0. Right? And how about that last one? What's that one going to be? X plus 3i equals 0. So obviously, zero product property would allow us to separate each of these binomials and set them each equal to 0. So I'm going to use zero product property backwards to put them together. Yay? All I did was put them together. And now if I really want the original fourth degree or third degree polynomial equation that's set equal to 0, I obviously have to do a lot of distribution and combining like terms, right? Once I distribute this binomial with that binomial, and combine all those like terms, it will give me the polynomial equation that actually produces these 3 answers, negative 5, positive 3i, and negative 3i. Now, the trick is to start with your complex numbers and the complex conjugate. Start with those. Why? Because I hope we remember from semester 1 that when you multiply a complex number by its complex conjugate, the imaginary values disappear and it becomes nice and beautiful. So let's actually do that. Let's distribute x times x, that's x squared, x times 3i, That's positive 3xi, or ix, whatever you want to call it. And then negative 3i times x, that's a negative 3ix, or xi, whatever you want to call it. And then negative 3i times positive 3i. A negative 3 times a positive 3 is a negative 9. But I times I is I squared. And I wrote it in red because we should remember that I squared is really what? Negative 1, back from semester 1, right? So we know that these middle terms are exact opposites. They're going to eliminate. And we know that this is really a negative 9 times negative 1, which is going to give us a positive 9. So what I have up here is really x squared plus 9. Does that make sense? Again, I just focus. I didn't mess with this one yet. I multiplied the complex number with its complex conjugate. The middle terms cancel out. That negative 9 times I squared, it's negative 9 times negative 1 to give me a positive 9. So I really have x squared, which is right there, plus 9, which is right there. So these two multiplied together gives me this beautiful binomial x squared plus 9. Are you with me? Now we still need to multiply it by this guy. So let's take the x plus 5. Just put it right here. X plus 5. We need to multiply it by the x squared plus 9. Let's do the work. X times x squared is x to the third. X times 9 is 9x. Moving on, 5 times x squared, that's plus 5x squared. 5 times 9, that's plus 14. No. Yes. No. What am I saying? Plus 14. It's been a long day. Plus 45. So the only other thing we could do to make this look nicer is to write it in standard form. Highest exponent down to smallest. So here's your correct standard form polynomial equation. X to the third in front plus 5x squared plus 9x plus 45. And of course, equal 0 would make that an equation that if you did solve, it would give you the three answers, negative 5, positive 3i, and negative 3i. Okay? If you were to graph this third degree polynomial equation in Desmos, you would see that it crosses only at negative 5, and it doesn't cross like a squiggle or doesn't touch negative 5. It actually crosses through negative 5 like a line because we know it's a single answer. And the other two answers to this third degree function obviously are imaginary. So let's do one more. Let's go down here to number 2. Okay, I obviously have these answers, and I need a polynomial equation that will give me those answers. What degree should I have in order for us to get those answers? 4, right? Because complex conjugate theorem says if I have a complex number as an answer, then its complex conjugate must also be an answer. So not only is it a 3i, but there's also a negative 3i that's an answer. So let's write these 4 answers way down here somewhere. X equals negative 2, x equals 1, x equals 3i, and x equals negative 3i. And we need to work backwards. So where did each of these binomials, or where did these answers come from? From what binomials that are set equal to 0? How about that first one? Tell me, what binomial set equal to 0 gives me the answer x equals negative 2? X plus 2. And the next one? X minus 1. And the next one? X minus 3. I, right? Don't forget the I. And the last one? X plus 3i. Okay? So what are we going to do? We're going to put these together, and we're going to have to multiply all of them. All these 4 different binomials. 1, 2, 3, 4. All these different 4 binomials. We need to multiply them together, combine like terms, do all that algebra 1 stuff, and then we'll be able to get our polynomial that actually produces these 4 answers. So even though they're all together, I'm going to choose to multiply these 2 first, and then I'll multiply these 2 first, and then I'll worry about multiplying both of my answers together. Make sense? All right, so let's begin with the complex number and the complex conjugate multiplying on. It's really easy. X times x, x squared. Actually, I'll zoom in a bit here. X times x is x squared. X times 3i is positive 3xi or ix. Negative 3i times x is negative 3i x or 3xi. Negative 3i times positive 3i is a negative 9i squared. So when we combine these middle terms, they eliminate because they're exact opposites. The I squared is really a negative 1. So again, I have negative 9 times negative 1, which will give me a positive 9. And we have, of course, this x squared. So I really have an x squared plus 9. That's my answer so far when I multiply the complex number with its complex conjugate. Let's do this other one over here. And I see a mistake. These binomials, when I put them together to multiply them, that should be a minus 1 right there. That was my bad. This is x minus 1. You can't see it. Okay, I apologize for that. But anyways, there it is. X plus 2 times x minus 1. Let's distribute x times x squared. X times negative 1, negative 1x. 2 times x, positive 2x. 2 times negative 1 is negative 2. So we still need to combine like terms. The negative 1x and the positive 2x, that ends up being just 1x. So I really have x squared plus 1x minus 2. And that's a quadratic trinomial that we get after multiplying these binomials. You guys get it? So we still need to multiply this trinomial with that binomial to get to the final polynomial equation. All right, so I am going to write these together. And I need to distribute, and I would rather distribute a binomial into a trinomial than a trinomial into a binomial. So I want to take the x squared, and I'm going to distribute the x squared. X squared times x squared is x to the fourth. X squared times 1x is 1x to the third. X squared times negative 2 is negative 2x squared. Now we're going to distribute the 9. 9 times x squared is positive 9x squared. 9 times 1x is 9x. 9 times negative 2 is negative 18. And of course we could combine the middle terms, the negative 2x squared and the 9x squared. That'll give us a positive 7x squared. So what do we have in the first two terms? We have x to the fourth plus x to the third plus 7x squared plus 9x minus 18. Ladies and gentlemen, this is the quartic polynomial equation. If you were to set it equal to 0, if you were to solve that guy, it would give you those four answers: negative 2, positive 1, 3i, and negative 3i. Okay? If you were to graph this x to the fourth plus x to the third plus 7x squared plus 9x minus 18 on Desmos, you would see that it crosses right through the value negative 2, right through the value 1, and then your other two answers obviously are imaginary, giving you a total of four answers to this fourth degree polynomial equation.